All right, example 1. Determine if the series is absolutely convergent, conditionally convergent, or divergent. First thing I would do is I guess the nth term test for divergence, and I know already, since the degree on the top is smaller than the degree on the bottom, I know it's going to go to 0 anyway, but alternating, but still going to 0. So that actually means I can use the alternating series test, because I know that I have an alternating series, and I know that this is decreasing, and the limit approaches 0. Those were all three things that I needed to use. So I suppose I just have to show that. I know that, well, I guess my a sub n would be n squared divided by n cubed plus 1. And then the limit I have to check or show that as n approaches infinity of this, n squared over n cubed plus 1, I have to show that it goes to like 1 over n cubed to 0. 1 over n cubed, not nn. So that would give me just what? 1 over n divided by 1 plus 1 over n cubed. This goes to 0. That goes to 0, so it's 0 over 1, which is just 0. So that part is satisfied. Decreasing, we know it's decreasing just because the bottom is going to grow larger than the top is going to grow. I suppose for this one we could say that f of x equals x squared divided by x cubed plus 1, and then f prime, show that it's negative. F prime of x. I said you might not be able have to do this, but it is kind of complicated, so I'm going to show it on this one. Low d high, so x cubed plus 1, low d high, minus high d low, 3x squared, all over x cubed plus 1 squared. Now my task is to figure out is this decreasing? So maybe what I will do is simplify some more. I know that this is always positive, and I know that my x values are always going to be greater than or 1 and bigger. So for this, what am I doing? I want to say I'll distribute, so I get 2x to the 4th plus 2x minus 3x to the 4th. And I don't really care about the bottom. Yeah, so 2x to the 4th minus 3x to the 4th. That's just negative x to the 4th plus 2x. And that means I can factor out an x. Maybe a negative x. I'm going to factor out a negative x. And then what do I get? X cubed plus 2. This is always going to be positive. Oh, no, minus. Right? Minus 2. So actually, for that first term, we're increasing, but then for the rest of them, we're decreasing, right? Because if we plug in 1, well, we get a negative number here. Negative times a negative is a positive, so that doesn't help. But after that, anything that's 2 or greater, actually 2, if we plug in 2, we get 0, so that's not even decreasing. Actually, 2 is fine, because 2 cubed, I didn't realize that. So anything that's bigger than the square root, so anything after 1. But all we really care about is that it's eventually decreasing. So anything after the square root of, or the cube root of 2 would actually work, but the cube root of 2 is really small. Anyway, it's 2 and on. It's eventually decreasing. That's what we care about. So the limit goes to 0. Great. Always decreasing. Great. There was 3 conditions. Decreasing, limit goes to 0, and what was the third condition? It was that this part had to be positive. And we know that it's positive already because we have an n squared. Well, I mean, we're only plugging in positive, so that's actually positive. And those were the 3 conditions. So that means By the alternating series test, this converges. So that's what we can say. I forgot to check if it converges absolutely. I never even did that. So I know that it converges, that's true, but I want to check if it converges absolutely. That means that I can take the absolute value of this, which just gives me n squared over n cubed plus 1, and yeah, I mean, I found out that this converges by the alternating series test. I just didn't find out whether it converged absolutely or conditionally. So I have to figure that part out. Because remember, to converge absolutely means the absolute value of this converges as well. Conditionally means that this converges, but the absolute value does not. So let's take a look. I think I'm going to use a comparison test. I'll get rid of that, so I'll make the denominator smaller. That'll be n cubed and n squared. So the denominator here is smaller than this, which means the whole entire fraction is bigger, and this is 1 over n. Oh, that doesn't help because that's divergent. So maybe I'll use the limit comparison test. And I'll still compare it to 1 over n. So let's do that. 1 over n. So both of those are positive and decreasing. That's great. And then I would have, what, flip and multiply. That would be n cubed over n cubed plus 1. And now if I take the limit of that, I know this diverges, and n approaches infinity. This approaches 1, which is greater than 0. So it means that this and that, when you put them in the summation, those series do the same thing. So this diverges, and that means, so we took the absolute value and it diverged. That means this converges, but like conditionally. So I kind of went about that in a backwards way. Usually it would be easier, and I should have done this, but I wasn't thinking about it. Usually you get a series. So these are the steps. You get a series and you're like, it's alternating. Well, I better check the absolute value first, because if you got that it absolutely converges, then you don't need to do the alternating series test. That's why what I did was backwards. So first step, take the absolute value and see if it's absolutely convergent. If it is, you're done, because absolutely convergent implies that this thing is convergent. And then if you get that the absolute value of it does not converge, like we did here, this is divergent, which means this is divergent. So if you get the absolute value does not converge, then try the alternating series test, and you have to check those 3 conditions. Your sequence is positive, and that's without this part, so you're ignoring that. So the sequence is positive, it's always decreasing eventually, that's what we found here, and the limit of the sequence goes to 0. If all of those are true, then this converges by the alternating series test. And we found that this converged by the alternating series test, but if we took the absolute value of that, it diverged by the limit comparison test. Thus, the absolute value diverged, the regular one converged, so this converges conditionally. All right, that was way too long of an explanation.